The name of that function is trim mean. Come on. Maybe I'm too close, I don't know. First of all, it's from 3 to 985. It has two arguments. The first argument is, what's your data? The second argument is, what's the total amount of trimming you're going to do? Surprise, surprise, it's kind of between them. You can change that number. That's why I kind of made it a parameter. Oddly enough, when that number is closer to 100%, you should get exactly the same thing as median. That's what a median is. It's 100% of the median sense. Or technically 99.99999. My own personal preference is using 1%, but so if you're going to pick one of these measures as a measure of reward, I tend to pick 1% trim mean, but we could also do 5. Now we need to worry about measures of risk. Yes, on average, on a trim basis, S&P is expected to make about 11.5% a year, okay, on average. That's actually a pretty healthy number. During that period, I don't think average inflation like about 3%. Or if you think about it, it outperforms the investment-grade corporate bonds by over 6%, which is pretty close to having very low risk. But did that happen for a reason? Yes, on average I do better, but are there cases where I'm doing much worse? For example, if I click on the whole thing, this little bar at the bottom of Excel sheet is called status bar. It actually gives you some summary information without actually you calculating it. Unfortunately, you can't make that any bigger. The weekly return from S&P 500 went anywhere from -20 to +13. On the other hand, for the bond portfolio, anywhere from -13 to +14. So it's not kind of as risky. Technically, I could calculate the range as a measure of risk, but that would be really not robust. Okay? So measures of risk, we're going to call this measures of deviation. So I have to get these back. Control Y redoes Control Z, which is an undo. Okay. I don't know why this doesn't happen to me at home. There is something at EKU, it's not just this room. Same thing happens to me in other rooms. It happens to me in 101, it happens to me back in the labs. But at home, no problem. The idea is just like mean is kind of a sense of what is a typical number. The measures of risk we're going to get are what is a typical number for deviation from that. Okay, there is one number. It's called standard deviation. This is square root of variance. And variance is average square deviations from the mean. It's kind of a weird measure. For each observation, you're going to calculate how much it is different from the average. You're going to square them, you're going to add those up, and you divide it by total number of observations, actually total number of observations minus 1, because those deviations have to add up to 0. Then you take the square root of that. The reason this is the most popular has to do with two things. One, his name is Carl Friedrich Gauss. It is related to the Gaussian distribution or normal distribution. For instance, Gauss was the big guy in math scene. This kind of won it all. And the other one that we're going to calculate, instead of calculating squares of the deviations, calculating the average, then take the square root, we can actually calculate the absolute value and average those. That one is called mean absolute deviation. Also known as MAD. That would be kind of the ideal measure. If returns were coming from a distribution that we call Laplace distribution, named after a French mathematician and statistician. But, you know, Gauss was there first, and Gauss was bigger than Laplace when it comes to statistics. But we have ways to calculate both of them. So I'm going to calculate standard deviation. The name of the function is stdev. And its units are the same as the average. These numbers are kind of big. I'm going to leave them as they are. I'm not going to multiply them with 52 because I only care about their relative magnitude. And the name of the function for calculating mean absolute deviation is fdev, short for average deviation. Should not be very surprising. Both of them are kind of non-robust, but at least on the standard deviation, I'm squaring those deviations first, adding them up, calculating the average, then take the square root. If there's a really big outlier, effect of that is really magnified. You have that in MAD as well, but not as magnified. And let's calculate it for all of them. Let's kind of see. As you can see, regardless of how you measure it, it looks like the corporate bond has about half the risk of corporate bond portfolio, has about half the risk of S&P 500, which is almost same as the gold, and the international portfolio seems to have a little bit higher risk. Okay? We can also do something similar. But I'm not going to do it here. Again, we'll develop those on Wednesday when we calculate a function when we develop a function for geometric mean. I will also create a function for kind of the trimmed equivalent of MAD. Instead of MAD, what MAD does, it calculates all the absolute deviations and it averages. Well, instead of averaging them, we could do a trim mean. Right? So that kind of would be a trim MAD, okay? As a kind of coming attraction, I'm going to leave it here. We'll take care of that on Wednesday, right? On the remaining 15 minutes, I'm going to kind of give you highlight for coming attractions. We want to solve the following problem. For a given level of reward,